Oh, this should say 10.1 confidence intervals for me. Apologies. There you go, corrected. Okay. So this was the formula for the confidence interval for a population proportion. So we started with a test statistic, or sorry, a sample statistic, and we added and subtracted a margin of error, and that had a critical value along with what we called the standard error. We called that the standard error instead of the standard deviation just because since we didn't know the population proportion, we had to use our sample statistic to compute it, right? Well, for a mean, it's going to be the same idea. We're going to start with a sample mean, right? Sometimes we refer to that as the point estimate. So you'll take a sample, calculate the mean of whatever it is you're trying to find from that, and then you'll add and subtract a margin of error. Margin of error will have kind of the same parts to it. It'll have a critical value, and then it'll have the standard deviation. But for a mean, the standard deviation involves knowing the population standard deviation. Well, if you don't know the population mean, it's really unlikely that you would possibly know the population standard deviation. So again, what we're going to do is replace that population mean with the sample, or the population standard deviation with the sample standard deviation. So if we don't know mu, we rarely know sigma either. And we can use the sample standard deviation as an estimate for sigma, but things don't work out as nicely as we might like. And so the idea here is that when you use the sample standard deviation and you try to create, say, a 90% confidence interval, we notice that if we do it over and over again, if it's a 90% confidence interval, what that means is if we were to take many samples and create confidence intervals out of those, about 90% of them should capture the true mean. Well, what we notice is that when we use the sample standard deviation, it's not 90%, it's much less. So our confidence level doesn't match the actual truth of what's going on. So we have to make an adjustment. So here they used a 99% confidence interval and they did it over and over again. Each one of those horizontal lines represents a confidence interval where this vertical line is the true value they're trying to find. But only about 92.5% of the 1,000 intervals that they created actually captured the mean. So it was much less than 99%. That they claimed, right? All right. So to achieve that 99% capture rate, we need to multiply by a larger critical value. But what critical value should we use? And the answer is we don't use a Z critical value, we use what's called a T critical value. And the T critical value comes from what we call a T distribution, which is similar to a Z distribution. A Z distribution is the standard normal distribution. But basically, a T distribution just has more area in the tails than the standard normal distribution. And there are infinitely many different T distributions. And so we specify the T distribution by what's called degrees of freedom. You don't really need to know much about these other than how to calculate it, and it's a very simple calculation that you won't have a problem with. All right, so, sorry, I thought they were going to give us degrees of freedom. Degrees of freedom are just sample size minus 1. So how many degrees of freedom a particular t-distribution has is sample size minus 1. Okay. So let's just jump right in. What critical value T star from table B should be used in constructing a confidence interval for the population mean in each of the following settings? Confirm your answers using technology. So when they say table B, it's a table that's in your formula packet. So if you have that formula packet that I printed out for you, grab that. I'll pull it up here. There we go. It looks like that. And then table B is going to be at the end. So here we go. Table A is your Z scores, your standard normal probabilities. And then here's table B, your T distribution critical values. All right, so I'm going to show you real quick how to do this by hand using this table, and then we'll go through how to use your calculator, which is more likely what you'll do. All right, so 95% confidence interval based on a simple random sample of size n equals 12. Well, for A, how many degrees of freedom will my T distribution have? So I said it's sample size minus 1, so in this case, how many would that be? 11. All right, so now let's go to our table. And the first column is your degrees of freedom. So we would go down to 11. And then you're going to look at the first row. The tail probability will be based on what level of confidence we have. So we want 95% confidence, right? So that means we want our T critical values to capture 95% of the area in the distribution. So how much would be left over in the tails? 5%. So how much in one tail? 0.025. So that's the tail probability that we'll look up. All right, so 0.025 is right here. That's our tail probability, and then we'll just go down to where those intersect. And our T critical value is here, 2.201. And so notice that that's bigger than the corresponding Z critical value for a 95% confidence interval. Remember, a Z critical value is 95% is 2 standard deviations away, right? And so Z critical value should only be about 2. In reality, it's about 1.96 if we use our calculator. So you can see that the T critical value is larger because, again, we need a larger critical value to actually get the correct capture rate for a mean. All right, how would we do this in our calculator? So let's pull up our calculator. Does anybody have a TI-83? Because TI-83s don't have this option, and you actually have to use the table, which isn't, as you saw, it's not crazy difficult, but you just have to get used to it. All right, so as long as you all have a calculator that's more updated than the TI-83, you can go to distributions, which is second vars. And then it's just that inverse T option, the fourth option. And the area is just the area in the tail. So that was the 0.025 that we came up with. And then you would just enter the degrees of freedom, which we said was 11. And then paste. And remember, the critical values are symmetric, so there's a -1 and the +1, and they're the same, right? Because you're going to add and subtract the margin of error. So pretty much exactly what we got, just a little more precise, which was 2.201. If I would have entered the full area to the left of the positive T critical value, which would have been 0.975, that would have given me the positive version of that critical value. Any questions about that? Oh, it's right above the 7. So if you don't get that menu that I got, if you just have this inverse T, yeah, it's area to the left, comma, degrees of freedom. All right, so try the next one then on your own. Now I want a 90% confidence interval from a random sample of 48 observations. So I'll give you a minute. See if you can come up with the correct T critical value. So first figure out degrees of freedom for that specific T distribution, and then give me the T critical value. Inverse T, I'm going to enter 0.95. How many degrees of freedom do we have here? 47. It's just sample size -1. As you get larger and larger sample sizes, the T distribution gets closer and closer to just a regular Z distribution. So you'll see in our table, and good, yeah, 1.678, awesome. You'll see in the actual table that they kind of abandon ship after a certain sample size. So you get to 20. And then they get to 30 and they start just going by tens. So if you were using the table, and let's say you had a sample size of 47, or sorry, 48 like we do, you would never round up to 50 because that would be acting like you have more information, a larger sample size than you do. You would always round down in that case to be more conservative. So the degrees of freedom for us, we would round down to 40. And then the tail probability is 0.05 we said here. So 40 and 0.05 comes out to 1.684, right? And so that's just slightly larger than the one we got, which is more precise. But that's because, again, we used less degrees of freedom, a smaller sample size in that case, so we were being more conservative. Therefore, we get a larger critical value, which is just going to produce a larger margin of error for us. All right, but you all have a calculator that's TI-84 or newer, so you can always just use inverse T. You don't have to use that table. But there we go. That's how we find the critical values. Okay, so let's talk about our favorite part of all of this, the conditions we have to check by hand all the time. Guess what they are? Random, 10%, and large counts. Random is the same. You have to know that the sample comes from random data. 10%, when sampling without replacement, the 10% condition ensures that our formula for the standard deviation is approximately correct because it just assumes basically independence among the individuals in our sample. And then large counts is different than that of a proportion. And we'll go over that. It's actually easier. When we were checking the large counts condition for a proportion, it was the n times p is greater than 10 and the n times 1 minus p is greater than 10. Well, in this case, we're not dealing with p, a proportion. We're dealing with a mean. So the large counts condition just ensures that our sampling distribution is normal. And so it's one of two things. Either you can know the population is normal, or your sample size has to be at least 30. And then the central limit theorem applies. So one thing I've said before, they're never going to try and do like a gotcha with the conditions, right? They're never going to give you a free response question that says, create a 95% confidence interval for the mean. And then the answer is going to be, gotcha, one of the conditions wasn't satisfied. You shouldn't have gone through that full page of work. But for a mean, sometimes you're given a situation where they don't tell you the population is normal, and the sample size is also not greater than 30. What we're going to do in that case is graph the sample. We're going to create just a box plot because that's the easiest graph to create in your calculator. And then you're going to sketch it out, and as long as there's no extreme skew, it's still going to be safe to proceed with T, what we call T procedures, which means creating a confidence interval or running a test, whichever one you're doing. All right, but let's practice checking conditions here. So this is just determine if the normal / large counts condition is met in each of the following settings. So A, to estimate the average GPA of students at your school, you randomly select 50 students. Here's a sample of their, here's a histogram of their GPAs. So this is a histogram of the sample that we took. In this case, n equals 50, which is greater than 30. So yeah, large counts is satisfied, right? All right. B, how much force in pounds is required to pull a piece of Douglas fir apart for each of 20 randomly selected pieces? All right, in this case, our sample size is less than 30, n equals 20, which is less than 30. They don't tell us that the population is normal. And also, this is a stem plot, so it's almost like a histogram on its side. What do you notice about the distribution of the sample? Not normal, strong skew, right? So I'm going to say strong skew in the sample. No, it wouldn't be satisfied in that case. All right. C, you want to estimate the mean SAT math scores at a large high school. Here's a large box plot of the SAT math scores from a random sample of 20 students at the school. So the sample size is 20, which is less than 30. But there is no strong skew or outliers in the sample. Like there may be a slight right skew. That's okay. It's very slight in this case. So we would say to go ahead and proceed with what we'll call T procedures. which is either creating a confidence interval for the mean or running a significance test. Oh, sorry. So ding, yes, we're going to say it's satisfied. And so this is just what I was saying. If the AP exam asks you to construct and interpret a confidence interval, all the conditions should be met. They're not going to do a gotcha question where they ask you to do that and the conditions aren't met. But you're still required to state them and show evidence that they're met. So that means that if the sample size is not greater than 30, you have to produce like a box plot and just state that there's not extreme skew or outliers, okay? All right, and we can use the 4-step process to kind of organize our thoughts on this same idea: state, plan, do, and conclude. And then we will create a confidence interval. We're going to do that here. So let's go to, we're going to construct a 95% confidence interval for the mean number of books read by all Americans in the previous 12 months. Oh no. That's going to be a solid round 0 for me, which is unfortunate. All right, in chapter 8, you learned about 73% American adults claim to have read a book in the previous 12 months. And this was based on a 2016 Pew Research Center study that interviewed a random sample of 1,520. The same study also reported that the average number of books read by the members in the sample, including those who reported 0 books, was X bar equals 12 books with a sample standard deviation of 18 books. All right. So let me write down just a couple of the things that we had there. We had X bar is 12. We had our sample standard deviation was 18. And our sample size was 1520. And what we want to do is create, so I'll do state. I want a 95% confidence interval for mu, which is the true mean number of books read by U.S. adults. Let's take a survey here. Sam, how many books did you read last year recreationally? Yeah. Solidarity. Grace? All right. Steffi? What was it? Oh, okay. Kaylee? Solid. Riley? Maya? Oh my God. And 2. Okay. All right. So we're nowhere near the mean in this class. I just feel like I'm wasting. I mean, look. I know I waste time when I like watch movies and stuff, but I can do other things at the same time, like scroll Twitter. Clearly important. You can't do anything else while you're reading a book. You just have to like put out a block of time and like.
Are you the type of person that has like a movie playing in the background? It's like it's there.
Yeah, I can't be alone with my own thoughts. That's crazy. I have to have like a podcast in my ears or a movie playing or something. All right. Here's the best part. We all agree. Let's plan. Let's state the conditions. So, random. It was stated as a simple random sample. So I'm just going to say stated SRS. All right, 10%. Just multiply your sample by 10. So for us, our sample size was 1520. So that times 10 is 15,200. And then I'll just say that our population is larger than that. So there are more than 1,520 US adults. Every year I've been, for like the past 3 years, I've been making a New Year's resolution. Like I'm going to read 10 books this year. I got 2 pages into my first book. I like went to Changing Hands at the beginning of the year and bought 2 books. One was like a Stephen King novel, and then the other was just like one of the employee recommendations. I got 2 pages into the Stephen King novel and have not picked it back up. It's still. That's true, but I'm always like, I'm going to start with 10 and I'm going to pick this huge book so I feel accomplished when I finish it. And I just get intimidated by it.
I remember the stuffing is in like elementary school, I'd get through like 50 books in like 2 months. Just like plow through them. But now it's like, yeah, I was never.
It's crazy like how much it helps to have that motivation. Like it's really annoying, like going to school and whatever, you know, you may think of it as annoying, or like you guys are maybe getting to the point where you kind of start to appreciate it because you're going to go to college and get to choose the things you want to study, which is sort of the equivalent of what Kaylee's talking about, right? Like it's reading what you like almost, but it is motivating because you look back at it as an adult and you're like, I wish somebody would tell me I had to read books right now so that I would actually do it. Or not. Yeah, it's weird to return to it, right? Because then like 4 days go by and I'm like, I can't go back into that. Like I don't remember what was happening in it. And I don't want to, God forbid, I flip 3 pages back and reread them.
Then you feel like you have.
Right.
I didn't learn how to read because I had serious issues with my eyes.
Yeah.
Pretty much all the way through 8th grade, I still like I went to many different eye doctors to figure out what was wrong with my eyes until finally I figured it out. But like I just couldn't read for the life of me when I was a kid. So I would get so confused. I think it was also some I don't know mental health things or whatever. I'm checked on that. But like I literally like couldn't read things because I was always have to go back and reread them because it would go 1 year out the other. Like mom up until like.
As our sample size is much larger than 30, it's 1520, right? So our conditions are good to go. And we're ready for the do step, which is we're just going to create our confidence interval. So normally, let's say we were doing this by hand. This is a 1 sample. This is going to be a t interval because we're using a t critical value for mu. I just want to go through how I would do this by hand one time. And by hand, I mean like if I were actually making the calculations, we're still going to use our calculator, but then I'll again show you how to use your calculator. So you would start with your sample mean, which for us was 12. And we're going to add and subtract a margin of error. But the first thing we need for that margin of error is a t critical value. So off to the side, let's find our t critical value, and we'll use our calculator again. This is a 95% confidence interval. So how much area in total is in the tails? Yeah, in both tails it's 0.05, in one tail it's 0.025, right? So if I wanted that t critical value, I would do inverse t. If we want the positive version, we can do 0.975. Just add the 0.025 to the 0.95. And then our degrees of freedom, sample size -1, so that's 15, 19, right? And so I get 1.962. So our t star is 1.962. All right. So I would do 12 plus or minus 1.962. And then I would multiply that by the standard error. Standard error is going to be this formula. Here we go. So for a population for one sample. Standard error is sample standard deviation over the square root of sample size. So that's our sample standard deviation was 18 over our sample size, square root of our sample size, so over root 1520. So there we go. That's the calculation that should actually get us our confidence interval. Let me do that in the calculator real quick. We'll go 12 minus 1.962 times 18 divided by root 1520. All right, so 11.09 to, I'm going to do the same calculation, but change it to addition. Plus 12.91. Great. So, conclude. We're going to use the same exact script that we used for a proportion, but now we're just going to do it for a mean. So we are 95% confident that the true mean number of books read by U.S. adults in the last year is between 11.09 and 12.91 books. I kind of set it in reverse, actually, of what I think I gave you the script as. It's fine. You can do it either way. But the script I would have given you last time was we are 95% confident that the interval from 11.09 to 12.91 books contains the true mean number of books read by U.S. adults. Just reverse order. Questions? Let's do it in the calculator because that's what you're normally going to do. Everybody do this with me so you get that kind of tactile practice. All right, so we're going to go to stat tests. Remember that I said if it's for a proportion, the name of the test will have prop in it. If the name of the test doesn't have prop in it, it's for a mean. So the one we want is a T interval, the 8th option. You will never use Z interval. The only time you would use Z interval would be if you knew somehow the population standard deviation, which you won't. So this is T interval. Yeah, all vaxxed? Yeah. Way to go. All right. It'll let you either put in raw data or statistics. In this case, we're going to use statistics. So I'm going to scroll over to stats. Thanks, Kitty. And then we'll just input the stats that we have. So our sample mean was 12. Our sample standard deviation was 18. Our sample size was 1520. And our confidence level we want is 0.95. And then we'll just tell it calculate. And there you go. It gives us the exact same confidence interval, 11.09 to 12.91. All right, let's do one more. but we're going to do it with raw data. And what I'm going to do is just have us on this one assume that the conditions are met, because we only have like 15 minutes. So let's do one more. So a manufacturer of high-resolution video terminals must control the tension of the mesh fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, too little will allow wrinkles, and the tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings for a random sample of 20 screens from a single day's production. And I want to construct and interpret a 90% confidence interval for the mean tension mu in all screens produced on this day. Now, is the large counts condition met? Do they tell us anything about the population being normal? No? Is our sample size greater than 30? No. What would we have to do to make sure that it's okay to proceed? Okay, so I'm going to walk you through that in your calculator. Let's go ahead and enter this data into list one in our calculator. And if you don't remember how to get there, hopefully you do. It's stat edit. So everybody do this, and I'll move my calculator so you can see the data. But enter all 20 pieces of data into your calculator. So all right, so once we have that data in, again, if we were checking conditions on this, we wouldn't just be able to say our sample size is greater than 30 or that we know the population is normal. So what we would have to do is graph the sample. So hold on. Oh, quit this. The calculator's in a different mode from Calc 2. Okay. Let me just clear out any other graphs that I have. All right, so we want to go to stat plot. So second y equals. I'm going to turn plot 1 on. I'm going to change it to the box plot, specifically the one that will show outliers if I have any. Make sure that your X list is the list that you have your data in. It's list 1 for me. And then you can just do a zoom stat. That's zoom 9. So here's what you would need to include on your paper. You would just sketch this box plot and include some scale below it. The easiest way to include a scale is just hit trace, and I would just draw like a horizontal line below it and mark on the horizontal line the 5-number summary. So I would put the min 233.5, 275 at Q1, 308.85 at the median, and so on. And that's the fastest way, I think, to produce a graph. Clearly, this graph has no strong skew or outliers, so it's going to be safe to proceed, right? And let's do just that. So now I'll quit. We'll go to stat tests. And which one do I want? T interval. Good. If it doesn't say prop in the name, then it's understood to be for a mean. We're doing a one sample T interval for a mean. And now in this case, our input isn't statistics, it's raw data. So I'll tell it data, then tell it where to find that data, which is in list 1. Frequency will just always be 1 for you. And then your confidence level, I think in this case we only want a 90% confidence level, right? Yes. So I'll change it to 0.9. And then just calculate. If you're using raw data, make sure that on the do step you actually write down what the sample mean and sample standard deviation were. And then just conclude. So we would say we're 90% confident that the interval from 292.32 to 320.32 contains, what are we talking about here? The true tension of the mesh wires that lie behind the surface of the viewing screen. Does that make sense? All right, I'm going to save, you know what we'll do is on Friday, I have an AP question that I just wanted to go over. So that's fine. I can have you run that in your calculator on Friday. And then the rest of the time Friday, I'll give you time for